So we're asked to evaluate this indefinite integral, and we're given a hint that a trigonometric substitution might be appropriate. So looking at what we have to work with, it looks like this substitution, x equals, and a is going to be 1, x equals tangent theta, is going to be our substitution that we want to make. And so it'll be important to think about what the derivative of x is, because that's the derivative of tangent x. That would be that's the derivative of tangent of theta. So using the chain rule, that's secant squared theta, and then d theta, derivative of whatever theta is. Okay, so if we let x be tangent theta, then it's important to note that the derivative of x is secant squared theta d theta. If you recall that from first semester calculus from implicit differentiation. Taking the derivative with respect to x of a variable that's not in terms of x. Well, the derivative of the outermost function is secant squared theta, and the derivative of theta with respect to x, we write that as d theta. So this is the substitution we're using, and while we're at it, let's move the 9 to the outside. We have secant squared theta over the square root of 1 plus tangent squared theta, and d theta comes from the dx that we had up top here. Okay, so now we can use a Pythagorean identity, which is kind of the big idea with trigonometric substitution with integrals. 1 plus tangent squared x is secant squared, I said x, theta. 1 plus tangent squared theta is secant squared theta. And so now this is like you have x squared, this is like you have x over the square root of x. If this is your x, then this is the square root of x. So when you subtract the powers, 1 subtracted by 1/2, it just leaves you with the square root of x. Okay, so that's the algebra for the next step. I'm going to simplify. This is the square root of secant squared theta. And if you're square rooting a square, you'll want to have an absolute value sign. Now in our text, when this comes up, we need the absolute value sign first because this is always positive. And if you're square rooting a positive number, you should always get a positive result because secant theta by itself isn't always positive. So what's kind of, what's the word? It's implied, though it's not clearly expressed. It's kind of late at night here, so I'm having a hard time thinking. It's implied that we're only looking on the on like one interval of one full period. So we're thinking about only positive values. Although you still want to know that if you're taking the square root of a squared, you should always have absolute value signs. So we're going to make this assumption that we're only dealing with the values of theta that are going to result in a positive answer here. So we'd want to restrict the domain to be really official with this problem. But if we have the absolute value, that's going to make the integral pretty tricky. And so this is kind of a tricky part too. This is an antiderivative that's not often memorized. The antiderivative of secant x, it can be proven, is natural log of the absolute value of secant x plus tangent x. And then plus that arbitrary constant c, because we have an indefinite integral. Okay, so that's our antiderivative. Now this is theta. It's in terms of theta right now, right? All this work has been done in terms of theta, but we want our answer in terms of x. So up here, our original substitution was x equals tangent theta. Right, so we could replace this with x, but we need to be able to replace this somehow. So what's often done is you can take your original substitution, manipulate it a little bit. We know that tangent can eventually turn into secant if we square, if tangent's being squared. Oops, man, maybe it is too late at night to be doing this. That was not a fair transition, right? We're squaring both sides, and I was thinking one step ahead. x squared equals tangent squared theta. So all I've done is I've taken my substitution and I've squared both sides. Now I can rewrite this. Let's see, 1 plus tangent squared. So this would be secant squared theta minus 1 using our Pythagorean identities. Or if you want to continue getting secant by itself, because that's our goal, right? We want to have something to substitute in terms of x. Secant squared theta equals x squared plus 1. Or to finish this out, this is the square root, and we should be saying absolute value, but again, we're making that assumption that we're only dealing with the domain where for which the function would be positive in its range. So secant theta is the square root of x squared plus 1. So now we have something to substitute here in terms of x. Okay, we have 9 times the natural log of the absolute value of the square root of x squared plus 1 plus tangent theta, which is x. Okay, I think we're done. Yeah, everything's in terms of x, so we've got the antiderivative.